All right. Good evening. Let's get started. So today we're going to, so this is basically the last week of lectures, and next week is just going to be review and final presentation. So for this week, we're going to cover something about dealing with the data. So today will be a little bit about collecting the data, a little bit about dealing with the various data issues, and that next lecture is going to be on the data visualization. Okay. Sure. All right. So throughout all of these courses, you have been learning how to do the data analysis. But of course, for any type of data analysis, the most important thing is the data. Without data, you can actually do anything. So so today we'll talk about first where you would collect that data. So usually there are several kind of data sources, right? So the first kind is the internal source, that the data is just already collected internally by you or by your organization. So if you're a business, if you work at Google, then the business would generate a lot of data, right? Or if you work at JP Morgan, you would have a lot of data about your customers. So all of that is internal data. Or if you do an experiment and collect the responses, and from the experiment, that would also be internal data. Second kind is the one that we most often see, which is external source, but it is already exists somewhere. And then you can either access it for free or you have to buy it. So things like the stock market, stock prices, or option prices, or the CompuStat, the firm level financial information, all of that all of that data is there. And then you have to just access it through words or something else. Okay. And finally, there is the external data source that also requires some collection efforts. So the most common example is web scraping. Okay, so you know that there is a lot of information on the internet, and all of that you could potentially get all of that just by scraping the websites. And that's a huge amount of data, but it's not the easiest thing to do, right? It's not as easy as just using some existing data source. So all of this could be useful in different types of question you are interested in. And in particular, the first and third kind, because the ones that are internal or require some collection efforts, because that's not available to everybody, right? So if you get your hands on those data sets, that could give you sometimes an advantage. So the other things pretty much is you already know how to do it, but the third one that requires some collection efforts, and in particular, web scraping. So that's what we will be talking a little bit about. So there are several ways in general to gather some data that is online on the websites somewhere. So the first way is called the API. So that's short for Application Programming Interface. And that is using already a pre-built set of functions that's developed by some company to access their services. So Google Map has API, Facebook and Twitter all have APIs, and usually you would pay to use that. So that's not what I'm gonna talk about today. Because once you have the API, it's pretty obvious how to use it. Second kind is called the RSS, which is short for the rich site summary. And this is also probably not as relevant to you. It's kind of applies to the news sites or the blogs, okay, which summarizes frequently updated online content, but it's all in the standard format. And the third one, which we will be focusing on, is just the general web scraping. So you could use software, you could use Python or something else, and then you can just look at the HTML file of the web pages. And then from those files, you could extract the information that you want. Because on a website, there are all kinds of information, and usually you're only interested in a part of it, right? So then you would have to extract the part of the information you are interested in from that big file. So how do we, well, so first, yes, question?
Sorry, Alex, can you just talk a little bit more about API? Because previously I heard about this definition, but intuitively, is it like a door or something that for service? Can you talk a little bit further about API? Thank you.
Well, so I have not personally used it. Okay, so I'm afraid I cannot give you too much information on that. But my understanding is that you can just pay for their services, and then you could have your query of what information you want, and then that would give you a file. But I don't know if any of you have used it, or
it's like a filter, right? It's like a filter.
Yes.
It's like a filter. I mean, when you pay for whatever money you pay for it, and then you can like abstract the information through the kind of filter called API. Is that the kind of definition?
Right. My understanding is that just that it does the web scraping for you, so you don't like load the websites and search on the websites by yourself.
Okay, thank you.
So it's just automates this process, and it could also like control the traffic. But I don't know if any of you has ever used it, and that maybe you could share your experience. But
so I've used the Twitter API before, and yeah, that's basically how it works. It's almost like they scrape their own website for you, except obviously they just let you access their database, because like before it gets to the website. The Twitter one is like they'll let you do 100 tweets per day or something for free, but if you want more than that, you have to pay by tweet or by 1,000 of tweets, something like that.
All right, thanks.
Right. Yeah. Basically, they don't want everybody to scrape their websites and have a ton of traffic. So that's their way of controlling how much you can scrape per day. And if you pay more, then you can probably get more. But once you have the API, I think it should be pretty easy. I think there are some online resources, but that's probably pretty straightforward. Okay. So why do we want to do web scraping? As I said, this kind of data, not everyone have access to it. Although in principle, everyone can see that right on the internet, but they would have to spend some effort. So if you do that, you could have an advantage. And also, there is just a vast amount of information on the website that is probably like from the Twitter. You could generate like the sentiment for some stocks, for example, that which is probably very hard to see with other data, like publicly available data. And for some companies, they may not have the APIs, and then you have to like write your own web scraping code, which I'm gonna give you a very small example. And once you have built that, you can automate that, and then it can scrape like hundreds and thousands of web pages for you. And it's also fun. Okay. But of course, there is also caveat. So there are a lot of regulations, right? So some websites would require that you don't do too much scraping to access their data set. Like this one is from LinkedIn, I think. Yes, LinkedIn. So it says that they give you access to services, but not through scraping, spidering, crawling, or other technology used to access the data without the express written consent of LinkedIn or its members. Okay, so then you have to abide by those rules. And first you have to, of course, check their terms and conditions and notice if there's anything like this. And then just try not to scrape the data too aggressively. And usually the rule of thumb is to act as a human. So for example, like 1 web page per second as a starter. So, and the third rule is that the layout of the website may change from time to time. So you should make sure that you always update your code as needed. Actually, for the example that I'm gonna show you next, I did it last year, but when I just look at it again today, something changed a little bit, right? So I have to modify that. Okay, just a couple more logistics before we begin. And there's also a file that you can see for actually all the websites that's called the robots.txt. So this is an example for Google. And in there, you can see some instructions and some information that you might need. Okay, now, before we talk about how to extract that information, we need to understand like how this information are organized, right? So all of these would be organized in the form of a HTML file. And this is just an example of a very simple HTML file. So you have all of these things. Those are called the tags. And there would be one at the beginning and one at the end. And then every document would start with this HTML tag and then end with another HTML tag. So everything will be between those two tags. And then first there will be a kind of like the title or heading of the document, and that will be between these head tags. And then after the heading will be the body of that file. So those will be between the body tags. And then it's like different layers, okay? And within that body, there can be different components, right? So the first, like the H1 that you see here would just be another heading of within that body, okay? So this is like the heading of the first section. And H1 through H6 is just the different levels of that heading. And then finally, after that, you could have the paragraph, which is the main text, and that could be within the p tags. And there are several other tags, as you would see, but usually, for example, in this case, if you want to locate this information of hello world, okay, let's say that's the important information that I want to extract. And then what you would do is just to look for the tags that's associated with it. So like in this file, for example, you can just look for where the p tag is, and then the information I want would be within those like between those p tags. And then you can tell the program to look for those tags and extract the information between those tags. Okay, so now let's look at a more realistic example. So let's say we want to scrape the Yahoo Finance. So I can show you on my browser. Actually, I think you already did this before, that you could also use the pandas to directly just download data from the Yahoo Finance if you want the stock prices, okay? But here I'm just using it as an example to illustrate how would you extract information from this website. Okay. All right, so can you see my browser?
Yes.
Okay. So let's say we want to scrape the information for Apple. And then we would go to this web page, okay? And then on that page, you can see, for example, the company name, the stock price. So this first number is like the closing price of today because the market already closed. And then that's the percentage. This is the price change and then the percentage change from the day before. And then this price is for the after hours. Okay, so right now the market is already closed. So all of these numbers is just fixed, right? However, if you go to this website during the day, during normal trading hours, then you would see that these numbers are fluctuating. They are like changing every second. And that's dynamic content, okay? So, and then for this type of content, we would do it a little bit differently, as I will just show you next. But here you could also see there's a lot of other information as well. Like their market cap, beta, bid ask price, and so on, average volume. And all of this information, you might, for example, you might only want the beta of this company, and then you could just extract this number from this website. So let's see how you would do that. So first, you want to view the HTML file of this web page. So if you are using Chrome, so I'm using Chrome here, and you could just right click on this web page and do like inspect, okay? And then let's say we want, so in this HTML file, you can already see that all of the information is stored here. And when you click on them, you can actually see all of the information. And then if we want to just look for where this number is, the stock price, and we could just click on that number and inspect, and that will locate that number for us. So it's the number you can see is here, right? 125.86. And then before that, you can see a tag, which is called the div. That is a tag for a division or a section. And then there's some other tags. And all of these information, we will, the thing that goes before this number, we will be using it to locate where this number is. Okay. So now, let me just show you how to do this. So if you go to lecture 6 folder, and then there's a Python notebook called scrape example. Okay. So for now, I can just view my screen. You don't have to run it on your own. And the package we're going to use is just called Beautiful Soup. And that's kind of the standard package for the basic web scraping in Python. And because, as I said, this is some kind of dynamic content, all of these numbers are changing every second. So here you would also need another. So this is actually slightly more complicated example than usual. Okay, so if you're scraping another website, you can it would be even easier than this. Okay, just waiting for this to load. But let me show you what comes next. So first, you specify what is the page you want to go to. So that is the page. Okay. So this page, I believe is you go to the page of Apple and then click the financials. And it will also show you the income statement of the company. So our goal here is to first scrape this number, which is the current stock price. And then to also scrape this table here, okay, which is the income statement. Okay, let's see how to do that. So first, okay, I think that's already loaded. So first you have your URL here. That is the web page that you want to scrape. And then open that HTML file from that URL. And then let's say we want the closing price of this company. So here, all of these are standard, but the ones that we need to specify is this part, okay? So this is the tag. That's where this price we're looking for is located between. And then something associated with that tag. Okay, so for example, for this price, we can see that it's in here. Okay, I don't know if you can see this, it's very small, but here you can see a tag that's this number is right here, 125.86. And right before that number, there's a tag that's called span. And then it says the class equals to something, okay? And then the tag you want to locate is the span tag. And then within that tag, it also specifies class equals to something. Okay, so you just copy that part to here, this TRSDU up until the IB parenthesis. And then if you do that, that will just give you that number, okay, which is the closing price. And then you can use this number for other things or just store it somewhere. We could also get the percent change, for example. That's okay, let's just do this as a practice. So let's say we want to script this part. We will locate where that number is. So it's about here. And then we can copy that part. It's also a span tag, okay. That part, everything else is the same except this class equals to something. So you can just copy that part here. And that gives you the percent, which is this number right here. And then we can just do one more. Let's say you also want to scrape the company's name. So that's the Apple Inc. right here. And here it's a little bit different because this is a different tag, the H1. So that's the same as our very simple example. That's a tag for the heading. And we can also just copy that part. Everything else is the same, except you have to replace with, this is an h1 tag, and then you also have the class equals to something, which is here. And then you would get the name, which is Apple Inc. Okay, so that's, if you want single information, you could do that. And then if we want to also extract the information from this table right here, and then first thing, we would also have to locate where that is in this HTML file. So it's about here. Okay, so you can see the breakdown is here. And it's after, all of this part is after this div tag, and then class equals to something. So here, it's a little bit more complicated, but the basic idea is that we would look for that div tag, and then the class equals to something. And all of this information, although they're slightly different, they all start with the dib something. Okay, so we would extract all of the information from those tags with the class looks like that. And then for these numbers, we also do the same. Okay, so if you look at the HTML file closely, you could just see the pattern there. And then once we have all of this information, we can just import that into a data frame. And that's what it does here. Okay, I have to run that first. Okay, so you can look at this example more closely in your spare time. But in the end, we would get a data frame that has this information from this table, and it will look exactly the same. Okay, so you have the first variable is the title of the item in the income statement, and then there's the numbers. Okay, and at different dates. And one last thing is that all of these numbers, although they're numbers, when you extract those from the HTML file, they're actually strings. So then you might want to just convert them to numeric values so that you could do analysis on that. And that would just be an additional step. And after that, you would get a data frame with this table that's scraped from this web page. And then all of these numbers is would be in a numerical format, and you could do analysis. So this would be just one company. And of course, if you are already scraping the website, you might want to do that for a lot of companies. So then you would just do this many times, and maybe not too frequently. So you can just put some pause in your code that you just scrape one company per second, something like that. But there, if you're doing it on a scale, there is also more advanced techniques, which I'm not going to cover in this course. But there's actually a lot of resources on web scraping. You can find that on DataCamp. You can find that on other websites. So if you're interested, there's plenty of places to learn more. Okay. So for the advanced techniques, the one we're just using is the most basic one called Beautiful Soup, but there's also other more advanced ones. So there's one called Scrappy, and if you're interested, there's this course in the data camp that tells you some basics of that framework. And then when you're doing this really on the scale, you might also consider using a proxy pool, which is basically changes your IP address so that you can get around the blocking a little bit. And then you want to also store your data somewhere and not all on the Python. Okay, but all of those are more advanced. And if you're interested, you could learn more from the data camp. Okay, so that's just a very brief overview of how to collect your data from the internet and how to do the very basic web scraping. Any questions? Okay. And then I want to talk about a few of the data issues and how do you deal with those. Because all of this, you pretty much will encounter all of these issues in every data set that you collect. Okay, and after you collect the data set, and between that and doing your analysis, whatever that might be, there's a huge gap in between where you have to clean your data, and that would sometimes be very time consuming. And then there's some issues that you would always have to be cautious of. And I want to talk a little bit about those. So the first one issue that you will often have is the missing data. So basically it's just for whatever reason, some observations will be missing. Okay, so you just don't observe the values of some variables for some people. And this can be due to a number of reasons. So for example, if you do a survey and then the values could be just randomly missing when they're being entered into the computer. So that would be the first example. And then second example, if you have a survey that asking people, have you ever done cocaine? And then even if they have, they may just choose not to respond to that question. So it's a little bit from the first one, right? The first one is just randomly missing, and the second one is not. And the third example is that when you're doing some study, and then halfway, you want to suddenly start collecting a new variable. Okay, and then if you take that whole sample, for the first part of the sample, that variable will be missing. Or there might be, like in financial data sets, sometimes there could be a change in the accounting standards and regarding the disclosure of the public firms. So sometimes firms may be required to report some information first, and then with the rules changed, maybe they don't have to report that anymore. And then after that, you might see that the variable is missing. So a lot of reasons for missing data. And in general, you can put all of this into these three categories. Okay, first is called missing completely at random. And what that means is the probability of missing in a variable is the same for all units. Okay. The second one is called missing at random. it sounds similar, but it's a little bit different. So it means that the probability of missing in a variable depends only on the available information. So you have a bunch of variables that you observe, and the probability of missing may be a function of these variables that you observe. And then the last kind is called missing not at random. So this is the most tricky case where the probability of missing depends on information that you do not observe, okay? And then that also predicts the values that are missing. Okay, and the first missing complete at random is of course the best case scenario, okay? Because if it's random, then it doesn't actually create any bias. So example of that would be every time when you enter some survey responses into the computer, and then you flip a coin, and then if it's head, then you enter it into the computer, and then if it's tail, then you remove it. So then with random probability, that variable is missing. Okay. And if you ignore that information, there's actually no effect on your estimates because you're just missing a random part of your sample. Okay. If your original sample is representative, then after taking out a part randomly, then the remaining sample would still be representative. So there's no bias whatsoever. And then you may decide you could impute the missing values if you just want to have a larger data set. And then we'll talk about how to do that later. And then the second case, missing at random, is what this means is that the probability of missing is a function of what you already observe. Okay, so for example, if you ask people, again, this is a survey. So the survey question is, have you ever felt harassed at work? And then maybe men and women would respond to this question at different rates, okay? And if they don't respond, then it's missing. So that probability of missing could be a function of gender. And then you observe gender in that survey as well. So then you could probably use gender to predict whether it's missing or not. Okay. So if you completely ignore this issue, then your estimate would be biased because now you have the sample which is selected from the actual sample. And then that may also make your predictions worse. And what you could do in this case is to use the information that you observe, in this case, whether it's men or women, and then use that to build a model and impute a value for this missing entry. Okay, so you can still do imputation here. And the third kind is missing not at random, which means the probability of missing depends on something that you don't even observe. Okay, so for example, if you do a clinical trial of some drugs, and then patients just drop out of the study because they experience some very bad side effect that was not measured. Okay, so why is this missing not at random? Because the probability of missing depends on their response to this drug, right, which we really care about, and which we also don't observe. So that's kind of tricky. It's unlike the previous case where we still see whether people are men or women, and then we can use that to predict how probable they're missing. Or like cheaters are less likely to respond when you're asking if you have ever cheated, right? So it's also selecting on this variable whether they have actually cheated. So that's the variable that predicts the probability of missing. However, we don't observe that. So then if you ignore this, your estimates will also be biased. And how to handle this, you can try to improve this just treating it as a missing at random. However, you will probably never completely fix the bias. Okay, so you would have to always think about how that bias would go. Okay, so then the first thing when you have a missing values in the data is to think about which of these three cases you're in. And if it's the first case, great. So you can not do anything and still get unbiased estimates, or you can try to impute and improve the power of the data. If the second case, then if you ignore, then it's biased. However, you could use ways to impute the values. However, in the third case, then there would really be bias in the estimates no matter what you do. So then you have to consider which direction that bias might go and how do you interpret your results given that bias. Okay. And then how do you deal with that missing data? First depends on which category you're in. Also depends on whether that missing value is in the response variable, which is the Y variable, or the predictor X variable. So in general, it's much easier to handle missingness in the predictor variables. Because if you have some value, right? Because all of our analysis is about predicting the Y variable from the X variable. If you don't even observe the Y variable, then that observation is probably not very useful, right? Even if you impute that, then you're imposing what the outcome would actually be. And it also depends on whether this variable is a quantitative variable or categorical variable. And it also depends on how much missingness is in that variable. So for example, if you only have very small percentage of the data that is missing, then you can either impute that, right, which is probably fine, or you can just throw away the data, which also doesn't create a big issue. However, if you have that some variable is missing for a big fraction of the data, like 70 or 80%, and then even if you impute that, you would basically imputing the values for most of your data, and that's not a good thing, right? Because most of the data you would actually be generating from some kind of model that may not represent the reality. So then you might just consider whether you could just drop that missing data or whether there's some issue in your data collection process. But in general, if you don't have too much missing, and if you are in the first two categories, missing completely at random or missing at random, then it's always a good idea to try to impute some of the values. So I believe you have already, so there is a DataCamp course that I had on imputing the missing values. So I think some of you might have already taken that. And it talked about some of the methods here. Okay, so in general, there are, I would say, 5 ways. There may be more, but these are the 5 main ways of imputing a missing value. Okay. First is you can just plug in the mean or the median or of that variable. So if the sales is missing, and then the average sales in my sample is 1 million, and then I just put 1 million in that missing value. Or if it's a categorical variable, then I just put the most common category. Okay, so that's the easiest way to impute missing values. Just put the mean or median or the most, like the mode of the data. The second way is a little bit more complicated. So on top of that, you would also create a new variable that indicates whether this variable is missing or not, and then include that variable as an additional predictor variable. Okay, so that new variable, of course, it's a 0, 1 variable. And then if you want to, so that variable will just be a 0, 1 indicator variable. And then you include that as one of your X variables. Third kind is called hot deck imputation. So here what you would do is for each missing value, you can randomly select a value from the ones that you observe. Okay, so if a firm has missing sales, then you just take the rest of the firms where you observe the sales and then just pick one of the sales randomly and use that as your imputation. So this is kind of like the idea is kind of like bootstrapping, right? So you are generating your data from the data that you already have. The fourth way is you could model the imputation. Okay, so this is one of the methods that the data camp lecture talked about. You could treat that missing variable as a Y variable, as an outcome, and then try to predict that outcome variable using the rest of your predictor variables. And then you can predict that variable using whatever model you want, right? You can do linear regression, you can do machine learning methods, you can do non-parametric or logit or whatever is fit for that variable. And then you just use your prediction as the imputed variable, as the imputed value. And finally, the fifth way is pretty similar to the fourth way, except that after you generate that prediction, you also add some random noise on top of that prediction. Okay. And why would we want to do that? Because the data will always have some noise or error, right? So if we want to mimic the data generating process, we should also try to predict the value, but also add some noise or error on top of that, because that's how our data is actually generated. Okay, so here just give you a very simple example. Imputation through modeling. You could do linear regression. As I said, you could do linear regression. You could do any model you like. But here, let's say X, you have this X variable that is not missing, and then the one variable that is missing, and then you're treating that as the Y variable. So using the X to predict the Y. Okay, so here X is a categorical variable. It's just different colors, but it's kind of ordered from most red to most green, and Y is a numerical variable. So here, what would you predict this value to be? Well, you could do, one thing you could do is like the nearest neighbor, right? So you just look at which color is closest to this color. For example, you could take the two closest ones and then take the average and then predict a value of 0.75 and then use that as the imputation. And this one, for example, it's between this and this. So you can take these two nearest neighbors and then take the average of those values, that would be 5.05, and then use that as the imputation. And then you can just replace the missing value with your prediction, okay? And that is your new data, and then you can do analysis on that new data. Okay, so you're just treating the, basically you're treating the non-missing part of the data as a training set, and then treating the missing part of the data as a test set, and then try to generate predictions on that test set. Okay. And this is comparing the fourth method with the fifth method, right? The fourth one is you have a deterministic prediction. For example, if you are imputing using a linear regression model, you're predicting this variable that is missing using the other variable, and then the prediction would just be a straight line if it's a linear regression. However, you could add noise on top of that, right? And then you would have something like the right figure. Okay. So not, I wouldn't say one is necessarily better than the other, but adding some noise would probably be more sophisticated if that noise is correct, right? Because the data will always have some noise. However, it's also subjective what kind of noise you would choose to put in there. And then you would have to also estimate what is the distribution of the noise. So that's also some additional choices there. So then it may create more complicated issues. Okay. Right, so this is an example of how you would do that in practice. So you have this variable that is missing, and you treat that as the y variable, and you're predicting that using a linear regression, for example. And then the first step is to fit the model to predict the variable that is missing from all the other variables that you do observe. And then predict the value from that model. And then finally add in this error by just randomly generating a random number from the normal distribution, okay? Where the standard error of that normal distribution is just the mean squared error of the model. And you could do this for even for classification models too. So for classifiers, like the logit model or the neural network, then the logit would predict the probability of whether you are in one category versus another, right? So then you can just generate the random category with that probability that you already predicted. And that is already imputation through modeling with uncertainty. Okay, and finally, what if you have multiple variables that are missing? Okay, so before we only talk about if you have one that's missing, then you can either replace it with the average or try to predict that variable or generate the prediction and add some noise on top of that. So if you have multiple variables that's missing, then you can do this through a iterative process. So first, you can impute the x1, which is the first variable based on the other variables. And then once you have the x1 already, then you impute x2 based on x1 and the rest of the variables, and then do it one by one for all of the variables. Okay, and then after you do this, you may still have some missing values. Then you just have to repeat this iteration again until you have completely filled in the data set. Okay. And okay, this is the last thing about imputation. So once you have already done that imputation, one thing you could do is just to treat it as the actual value you have in the data, and then do analysis on that data. However, you may not want to do that because the part of the data that is imputed is still a little bit different from the original observed data, right? So you might want to treat these two parts of the data a little bit differently. Okay, and especially when you're doing the imputation through the prediction and then add some errors, then when you estimate your models using that imputed data, it might overfit to the just random noises in the imputed data, which you never want to be the case, right? Because those are just coming from the imputation. It doesn't carry any information about the data itself. Okay, so what you could do is a process called the multiple imputation. And what that is to rerun the imputation algorithm many times, okay? And then refit the model on the response many times, and then average the predictions or estimates of the beta coefficient to perform the inferences. Okay. So basically the idea is to, if you're doing the last imputation of imputation with a prediction and some uncertainty, then every time you do it, you might get a different imputed value, right? And then you do that many times and then take the average. And that, by averaging out, you would averaging out the noises also. Okay.
It's like
so,
bootstrapping, right?
kind of. Yeah, bootstrapping is you are generating bootstrapped data from the data and then get a beta for each bootstrap data and then look at the distribution of that beta. Yeah, so it's kind of similar. So here you are running the imputation model many times and then have a beta for each imputation and then look at the distribution of that beta. Yeah, you're right. Okay, so that's the first issue. So you can see it's a pretty simple issue of missing data. However, there's already a lot to think of, right? You need to think about whether which category this is in, whether that's missing at random or not random. And then if you decide to do imputation, you need to also decide how to do the imputation. And there are many ways to do it. And each of them might give you slightly different results. Okay, or in some cases, you might decide not to do imputation at all. But like in the exercises in the class, sometimes we might just drop the data set that is missing. Okay, so sometimes doing that is okay, but sometimes it's not. So all of these issues you need to think about. Okay, second kind of data issue that I want to talk a little bit about is that you have sensor data or sample selection. Okay, so it's a little bit related to the first issue, and especially the missing not at random. So censoring, we already seen this in the survival analysis, right? So if something is censored, it means that for a range of that variable, you do not observe. Okay. The first example is just the censoring in the survival analysis. So if someone the duration is censored, that means you only know the duration is longer than something. However, you don't know the exact value of that duration. Okay, so it's censored at that threshold, and you only know a range of that value, but not the precise value. Or example two, if the price of something, let's say a cryptocurrency or any stock, if it's negative, it would be censored at 0, right? Because there would be no price that's actually negative on the market. So that's also a type of censoring. Okay, and then when you run the regressions on the censored data, if you don't control for it, it will lead to biased estimates. Again, we have already seen that in the survival analysis. If you just throw out the people who are censored, that would create bias. If you only take the censored values, that would also create bias, right? So then you have to do this Cox proportional hazard model and estimate the partial likelihood, and that will give you the best prediction. But in general, any data could have some variable that is censored, and then you have to deal with it in a similar way. Okay. For example, if we are interested in some variable y, and this y variable is just a linear function of x. Okay, so this is just the most basic linear regression where you have beta x plus the error term epsilon. However, we don't observe the value of this y star for everybody. And for some people, it is censored, which means, for example, if y star is greater than 0, if it's positive, then we see the actual value. However, if it's negative, then we only see it's a 0. Okay, so this thing is censored at 0. This is the second example that we're talking about. If you're predicting the price of something, and you may see a lot of things have price 0, but actually, if they could go negative, they would be negative. So now, how do we predict like beta from these data that we have? Okay. So we know that if you only take the observed y star and the zeros, that would give you a biased estimate. And then the thing to do is the maximum likelihood, okay? Because for these censored values, you can still calculate the probability of the value in that range, okay? Even if you only know that it's in some range. So for example, in this case, if this y star has a distribution with the density, the PDF is small f and the CDF is big F. And then if y star is greater than 0, we see the actual y star. So the probability of that is just the PDF, okay? And then if y star is smaller than 0, then we only know that it's smaller than 0, okay? Because what we see is just a 0. And the probability of that is the probability of this y star being smaller than 0, which is the CDF at this point 0. Okay. And then we can calculate that log likelihood for everybody. And multiply them all together, that would be the joint likelihood. And then you can take the log, that then it will be the sum of everybody. And this likelihood function will be a function of your parameter beta. And then you can choose the beta that maximizes this likelihood, right? So that's what maximum likelihood estimation does. And then that gives you the estimate for beta. So this is kind of similar as what we did for the survival analysis, like the parametric approach, right? So for the parametric approach, we can also assume a functional form, okay, which gives us these numbers, the probability distribution of y as a function of beta and x. And then we just choose the betas to maximize that joint likelihood. Okay. And then you would calculate this likelihood differently for people that are censored versus not censored. If it's not censored, then it's PDF. If it's censored, then it's the value in that range, which is usually the CDF. And another thing that is related but not exactly the same is called the truncated data. Okay. So here, it means that for censored data, even if it's censored, you still see those data. Okay, you still see that their duration is 5 years, is cut at 5 years, and you know it's longer than 5 years, but you still see that data point. But if you have a truncated data, then you just don't see that data. Okay, it disappears from your sample. And then this is kind of related to the missing not at random, right? If you have a clinical trial and people are missing because their survival is really short, and then it means that the data is truncated if they have the y value is very small. Okay. So in this type of data, for example, we would see that the y equals to y star when y star is positive, but when y star is negative, we don't see the data at all. Okay. And this, of course, is even more complicated, right? Because seeing that data at least still gives you some information, but if you don't see it, you don't know how many are out there, right? So the thing, well, example of that is the survivorship bias, right? So this is this famous figure of an airplane. Does anyone seen this?
Yes.
What do you remember what it means?
So if you were to ask somebody where on the airplane we should reinforce, you might be inclined to pick where the red dots are. But because you observed this data point, that means the plane made it back and they reinforced the right areas.
Exactly. That's so you basically explained the story for me. Okay, so this is World War II. And people are trying to determine which part of the plane to reinforce to add additional armor. And then these are the planes that come back, and you can see that all of these places are being hit, right? And then if you just take that to be your sample, you might decide, okay, these are the places that get hit most often, and then we want to reinforce those parts. However, here you have a truncated data problem because you don't see every plane. Not every plane comes back, right? So the planes that don't come back are the ones that's being hit in the places that you see less often here. And maybe if you are hit in those areas, then it becomes really fatal. And then what you should reinforce is actually those parts. So you can see that if you have a truncated data and if you don't consider that issue, then it will give you a very biased estimate. So whenever you have something, whenever you suspect that maybe truncated data issue, you should always seriously consider that, okay? Otherwise, it will give you completely wrong conclusions. So how to fix that? If we suspect that's true, or if we know that's true. So here it's still maximum likelihood, okay? So that's always a fix in this type of sample selection or sensory. So let's say Y star have a density of a PDF of small f and CDF big F. And then what is the likelihood? Well, the likelihood is the PDF of Y star, right? Because if it's positive, then we see their actual value. However, that is conditional on that this Y star is positive. And that's because we only see the Y star when it's positive. Okay, so all of the things we see is conditional on Y star being positive. And the probability of that, and this is a conditional probability, would be the PDF of Y at this point of Y star divided by the probability of Y star greater than 0, which is the CDF at 0. Okay, so then this conditional probability would be PDF of Y star divided by CDF at 0. And then that's the probability you have, okay? Because again, our data is a conditional data. So then the likelihood is also a conditional likelihood. And what we do is to maximize that conditional likelihood with respect to the parameters. Okay. And then you can still get unbiased estimate for your parameters and use that to do prediction. All right, there's another way to fix this. This is more parametric, but all of this is parametric to some extent, right? Because if you want to do maximum likelihood, you always have to calculate this probability density of function of y. And if you want to calculate that as a function of x and beta, then you always have to assume some functional form y as a function of x, and also assume some distribution of that error term. Okay. So all of this will be under some parametric assumptions. So another way we could do is to say, so this is called the Heckman two-step. This is developed by James Heckman, who actually won the Nobel Prize in economics because of this discovery. Okay, so this is a pretty important discovery in economics. And what this does is to try to correct for the biases that's coming from a truncated sample. And the truncated, the condition for truncation is still if Y star is positive, you see that. If Y star is negative or 0, you don't see that. So the underlying relationship is a linear one. Okay. However, you only see the Y star conditional on its positive. And the expectation, in this case, the conditional expectation, conditional on Y star being positive, is the beta x plus the expectation of this error term epsilon, conditional on Y star is positive. Y star is positive, which means beta x plus epsilon is positive, which means epsilon is greater than minus beta x. Okay. So then you have the expectation of epsilon conditional on epsilon is greater than something. And then you could calculate that if you assume that epsilon has a normal distribution. Okay, so if I say that it has a normal distribution with standard error sigma, and then epsilon by sigma just have a standard normal distribution, and this term would be the expectation of something with standard normal distribution conditional on that something is greater than some number. And this number, we can calculate that, right? So then this would be a fixed number that we can calculate once we know the value of the beta, once given the value of beta x and sigma, and we know that distribution, which is normal. And then what you do is to calculate this value. And add that into the regression as additional predictive variable. So the first, so this is called the two-step estimation. The first step is that you can estimate a probit model. Okay, probit model is where you predict something that is 0 or 1, and this thing you're predicting is whether yi is greater than 0 using all of the observations. And then you can just run a linear regression of y on both x and this term that you calculate from the data. And all of this is relies on the assumption that the errors have a normal distribution. But once you assume that, then you can just do a simple linear regression with this added term, and then you can still get unbiased estimate of beta. That's kind of the idea. Okay. Any questions about this part? Well, so this is the second class of data issues where you have censoring or truncated data. So censoring we have already seen in the survival analysis, and that is actually the main reason why we're doing survival analysis instead of the more classical models for the durations data. And then in both of these cases, you would do the maximum likelihood, which can correct for that selection or censoring. Okay. Well, there are, of course, a bunch of other data issues, but we have already also covered them at various points throughout the semester. So we already talked about missing data and sample selection and censoring. And then the other issue, of course, is outliers. And thinking one of the examples we did this process called Winsorize, which is to cut out the top and the bottom tail of a distribution. Okay, so for example, for anything that's above the 95th percentile, we replace them with the 95th percentile. And for everything below the 5th percentile, we replace them with the 5th percentile. And that would allow you to just restrict the impact of the outliers and making them more bounded. And that will usually make your estimates more precise because you're reducing the noise that's coming from the outliers. Okay. However, you might say that outliers is also a feature of the data, right? So we don't want to, so sometimes maybe outliers also represent the relationship also to some extent. So that getting rid of them, which also might create some bias. So then you might probably want to see how the results look like, both before you windsorize and after you windsorize. And if they're kind of similar in terms of the estimates, but maybe after windsorize, it gets more precise, right? And that's kind of the ideal situation. You know that it's not biased, but this process of windsorizing reduces the noise. However, if they're really different and maybe outliers is creating some bias, or maybe removing those outliers creating some bias. So you need to think about that. And then other issues. So sometimes you have big data, right? Big data means a lot of observations and a lot of a very high dimension. Okay, so both a very big P and a very big N. So N is the number of observations, P is the number of predictors. And if you have a very big P, then you have this problem of high dimensionality. And then the problem there would be overfitting, right? So I think you have already talked about a lot of that in the machine learning class. So you would need models to correct for that and also avoid the multi-collinearity problem. And then the ways to deal with the high dimensionality, I believe this you should already talk about those already. So you could do model selection like the BIC and AIC. You can do regularization like lasso and ridge regressions, okay, which is to penalize the number of variables you include in the model. Or you could do principal component analysis where you sort of aggregate the large number of X variables into several dimensions. Okay, and when you have so big N and big P are usually very correlated, right? So if you have a very large sample size, and then you can afford to have a bigger number of variables, okay? And if you have a smaller sample size, and then you would want to reduce the number of variables even more. So there's no absolute criteria for how big P should be in your model, right? It all depends on how big your sample size is. And when N is big, okay, then from a statistics point of view, this is usually not a problem, but it's mostly a problem from the computational perspective. It just takes forever to run some data. And then I think you've probably already seen the problem set, right? If you have a somewhat big data set, it's not huge, right? You have probably a few thousand firms and their earnings announcements. And then when you running a non-parametric model like the kernel regression on that data, it's already taking a while. So then in those cases, you could have really big data sets, and then what you would do is to perform some preliminary steps on the subset of the data set. Okay, you could take 10%, for example, at first. And also, by the way, the problem set, if you are having issues just finishing that running the kernel regression on the big data set, then you could also restrict to part of the data set and just like 10% random sample, and then just do analysis on that 10% random sample, as long as your code for for the analysis is correct, you would still get full score. Okay, doesn't have to be the exact same result. Okay. But you'll have to always keep in mind that having a big data doesn't solve any problem. Okay, so it's usually great to have a very big N and a larger sample size, but they're saying that if you have garbage in, then you have garbage out. So if your data is not representative of the population, then whatever fancy model you do, you might still get very biased results. So all of these issues we talk about are still present, right? No matter how big data you have, you could still have censored variable, sample selection, missing data, and all of that you need to deal with. And in the end, what you want to make sure is that data is representative of the population. Okay, so when we collect that data, we should also keep that in mind, that the best data is always a random sample of the population that you want to study. And sometimes you might even want to sacrifice your sample size just for the representativeness. So then there's the question, if you have a 5% random sample, and if you have 90% non-random sample, which one is better? And it's not clear, right? In one case, you have representativeness and probably less bias. And in the other case, you have much more data, you have much more power to estimate everything. So if you're interested in that, there is a pretty great YouTube video that you could watch that talks through some of these issues around the data representativeness. Okay, and all of these things we talk about, right? The missing data, you want to, when you do the imputation, you want to make sure that the data is still representative, right? The truncated data means that the data is not representative, because part of that data is the sample is selected based on the Y variable, so that it's not representative of all the Ys that could be out there. So this is something to keep in mind, whatever data you work with. Okay. Any questions? So that's all for today.
Professor, I saw a course related to cleaning data in Python. Can I do that and as the 5 course I did?
Sorry, I can't hear you very clearly.
Can you hear me now?
A little bit better.
Oh, okay. Yeah, is that like